everybody. Today it is my pleasure to introduce to you Rasmi Hajjar. He's a PhD student at the Instituto de Física Corpuscular in Valencia, a university in Spain. And today he's going to talk to us about the origin of the cosmological neutrino mass by 2 points of view: background and perturbations. So feel free to get started whenever you want, Rasmi. Thank you again for joining us, and we're looking forward to hearing from you now.
So thank you, Enrico, for accepting me for just to give this talk here. And yeah, I mean, as you said, today I'm going to talk about a little bit about the cosmological neutrino mass bound and try to shed some light on this measurement that lately we've seen a lot of things going on about and even a growing tension in that I will mention shortly. But I mean, since I'm a neutrino physicist, I will start at the same point than everyone that is mentioning the 2015 Nobel Prize, in which we found out that neutrinos detection and production states were not the same as the vacuum transport ones, where the detection and production states are called flavor states, and the vacuum transport ones are the mass states. And the discovery of neutrino oscillations that was awarded by this Nobel Prize that I mentioned just helped us to measure two of these different mass splittings between these three massive states, and therefore it implied that at least two neutrinos are not massive. However, the situation is not clear in the neutrino mass sector at all, because since we are only sensitive, for example, in the delta M31 parameter to the absolute value, we don't know if the nu 3 neutrino is the lightest one or the heaviest one. And this opens the possibility for two orderings that are the normal ordering, in which the lightest neutrino is the one with the highest electron content, and the inverted ordering, in which the lightest neutrino is the one with the smallest electron neutrino content. Now I'm telling this because we know these two different splittings, but we don't know the absolute scale of neutrino masses. This is an unknown parameter, and right now the most stringent constraint comes from cosmology, and this will be the main aim of this work, to see what's going on with that bound. So for these two different orderings that I just mentioned, what we can do is generate a function in which we obtain the sum of neutrino masses as a function of the mass of the lightest neutrino, that is the unknown that we don't know. And as you can see, thanks to the two measurements given by oscillations for these two orderings, the plot looks like this, where if the mass of the lightest neutrino is high, it increases more in a linear way. But then if it goes to zero, it tends to a value that in the normal ordering case, it's 0.06 electron volts for the sum of neutrino masses, and in inverted ordering is 0.1. And we just know these lower limits from oscillations, but do we have any other measurement on this parameter? And the first one that I'm going to mention is the Catherine 2024 limit, that it was shown in the Neutrino 2024 conference, was updated, and now the limit on the sum of neutrino masses from Catherine measurement is 1.35 electron volts, which, as you can see, it's pretty far from the most pessimistic scenario, in which one of the neutrinos is massless. So this is the living measurement that we have made at a lab, but we have the possibility to just in cosmology, since the sum of neutrino masses is a fundamental parameter that affects cosmological evolution, we can try to see what cosmological observables tell us about this parameter. And in order to do so, the first fundamental measurement that everyone thinks about is the CMB measurement done by Planck 2018. And yeah, with this, you can see that this limit is much better than the Catherine one, and only including CMB measurements. If you then start combining different data sets, you can get even lower and lower. So for example, if you include to this CMB measurement the BAO measurement, you get to 0.12. Recently, since from the latest DESI BAO result, if instead of standard BAOs that were used before, we include DESI, we get even to a level that is 0.07. So it goes below the inverted ordering lower lower value by oscillations. And if you see there are a lot of different works, since this has been like widely studied in the literature, but if you have for certain combinations, you can even go below the normal ordering limit, which is 0.06. And I'm citing, for example, this paper, but there's like a lot of papers that go below this value. So the thing is that here you can clearly see that there's a huge, attention is starting to show between the oscillations measurements and what cosmological observables are trying to tell us. And the situation is even more critical if we, like I'm showing, for example, this plot that you can find in this paper. And here what they do is just trying to quantify this tension between cosmological observations and oscillation measurements. And for a lot of different models, and also focusing on normal ordering, inverted ordering, and different also statistical ways to compute this tension, in the end, we can see that, like, for some cases, maybe it's at the 2 sigma level, but all of them are between the 2 or 5 sigma level of tension between the cosmological limits and oscillation and terrestrial experiments. And therefore, here, cosmological data is growing and growing, and the situation seems that it's gonna like get worse and worse. But yeah, and here, in light of this situation, like we wanted to understand a little bit better, like where do these cosmological bounds come from? Since this cosmological measurement is an indirect measurement, and like the way to compute it is like cosmological measurements come from cosmological observables that are prediction of the Einstein equations. These Einstein equations give us two different sets of equations that are the average energies ones through the Friedmann equations that would be called background evolution. And then if you perturb these Einstein equations, you can find also the perturbations level of the cosmological evolution. And here in this regard is where we want to focus on two different aspects, because we find the background evolution of the average energies as like an energetic input, and the evolution of these perturbations as containing some kinematical imprint of the effect of neutrino masses. And so, yeah, the question is very simple. So what is cosmology measuring? Is it measuring something related with the energy, in the sense that we are measuring if neutrinos behave as matter or as radiation, or whether the neutrinos undergo the under-relativistic transition or something like this? Or is something like the free streaming scale, which is a kinematical imprint that neutrino masses have on the cosmological evolution? So in order to start, I'm going to focus on the background part. And here I am showing the different relative energy density content of the universe as a function of time. And as you can see, like photons, dark matter, baryons, and everything behave as expected. And we have here a band in neutrinos. These band in neutrinos tell us the behavior of neutrinos that start with a radiation behavior. And here, the measurement of Catherine tells us that they behave as radiation until the CMB at least. But then we can try to also think of that we don't know this parameter, and if the sum of neutrino masses is 0, they will behave as radiation until the end, until today. But they can have a different, well, they can have a value, and then if the sum of neutrino masses has a particular value, they will undergo the non-relativistic transition, and they will behave as matter at some point. So you can see that the main difference that neutrinos induce is a difference on the energy budget of the universe, having more if the neutrino masses is higher, and that implies that if they imply more mass imply a faster expansion of the universe. And this is the main background effect. I just wanted to show for completeness the two Friedmann equations that contain like the equation of a state parameter, which determines the density, the neutrino energy density evolution. And just this parameter is the one that could like make here the step of going from radiation to matter happen before or after. And here I'm showing, for example, the equation of a state of neutrinos as a function of the scale factor. And as I said, Catherine says that this transition happens around recombination. And then we also included the bound of the CMB here that happens a little bit later, and the lower limit set by oscillations that it will be even later. But this is just the shift on this step is the only background effect, the real background effect on neutrino parameters. Now, if we go to perturbations, this is a more complicated process, but they are solved in an iterative way in time. And basically here, what I want to say is that you have different neutrino sources. These neutrino sources are the density contrast, velocity divergence, and the isotropic and anisotropic momentum flux. And you basically input this into the perturbed Einstein equations. And you also give the different sources evolution thanks to energy momentum conservation. And you start solving all of these. So it's a closed system with the only thing that you have to also set up the initial, well, the way to compute the sound speed in this case, or the isotropic momentum flux, or also the anisotropic momentum flux or the shear stress. So these two parameters are the ones that could be modified, specifying a different neutrino model. And yeah, for different models, they can change. So how will they change? For example, if we focus on the sound speed, here we wanted to see like if there was a big scale-dependent effect, but I am just showing the different sound speeds for the different masses as I'm showing here as a function of the scale factor. And if we choose two different modes that are really far apart, you can see that there's not really a big change between one case and the other. So we consider that this is not like a huge scale dependent effect, and trying to see like to measure the neutrino masses from this parameter is not going to be viable. However, if we focus, for example, on the anisotropic stress, we can see like a very prominent feature due to the free streaming scale of neutrinos when neutrinos stop free streaming and they start clustering. And this can be seen as a function of time, for example, in a way in which we show for a particular mode that when that mode crosses the free streaming scale set by each particular mass, they start going to zero very rapidly. And yeah, as the higher the mass, it happens before in time, as you can see like these vertical lines here. Or also, for example, if we fix the time and we say that we are today, we can see that there's a peak shown on the K spectrum of the anisotropic stress. So basically, this is the main feature that will help us to put a robust measurement focusing on kinematical imprints of neutrino masses. So I mean, we can talk more about this later and about all the details, but I mean, the point is that basically the anisotropic stress has, I mean, you can see this feature on the anisotropic stress and try to see if this is what you are measuring. So now that I've explained a little bit like the different parameters that govern the background and perturbations evolution, I'm going to just tell you about what we did. And what we did is basically just introduce two parameters that are the background mass and the perturbations mass. And in the standard case, these two parameters are equal. But here, what we're doing is the background mass just generates the equation of state in the standard way. So like we generate the equation of state of neutrinos like we do in the standard case, but it is not the same mass parameter that generates the shear stress or the sound speed that I'm showing here, although these two are also generated in the standard case. So what I'm saying is that these two masses are not the same. We generate things also in the standard as in the standard case, but they are not the same mass, so they can change independently. And now, just to see a little bit more how these masses work, we're going to focus a little bit on the CMB spectra just to see the different effects that arise. And this is the main spectrum that here I'm showing three different scenarios, but what I'm showing here in green is just the CMB spectra for massless neutrinos. Here in the panel below, I am showing the relative difference with respect to this massless case. And the red line is the case in which we only have a mass of 1.35 at the background level and 0 at the perturbations. The blue is the opposite, so 0 at the background and 1.35 at the perturbations level. And the purple is the one showing like the standard case in which both masses are the same. So here I'm going to focus on 3 different regions because the effects are relatively different. So for low multiples, I'm not going to tell, there's some effect at the level of background, but since they have tiny constraining power, here the effect is not, when it will not be seen at the level of the results. So, but there's a background effect, and you in the paper is all stated, and you can learn more about it. Then if we move to the intermediate multiples, here what happens is that the perturbations mass and the background mass have opposite effects. And the thing is that, as I said, background mass, higher background mass like makes a faster expansion of the universe. Since gravitational potentials are decaying, they make them decay faster. And then a faster decay of the gravitational potential will induce a higher anisotropy at this level. And that's why the red line is higher compared to the massless case. And the perturbations mass, increasing the perturbations mass, will lead to the opposite effect. So we will have higher clustering, less decay of the gravitational potentials, and therefore like a suppression of the anisotropies at this level. Now, if we move to the higher multiples, here we have that the main effect here is that the diffusion damping is governed by background quantities, and therefore this is governed by the background neutrino mass. And in order to see this better, we can focus on the unlensed spectra, in which I just remove lensing from the equation now, and I'm showing that like if you have 0 perturbations mass or 1.35 perturbations mass, but the same background mass, like the lines almost coincide. So there's no effect there. And the only effect is for the unlensed case, the damping scale that is changed by the background mass of neutrinos. And just by reducing the background mass, you're just moving these lines towards the massless case, which is the one that I'm showing in blue, even though it has 1.35 for the perturbations value. But yeah, it will be linear going to 0 in this way. But since you can guess also from the previous slide, I mean, lensing has also a fundamental effect here. And basically the same effects that apply at intermediate multiple level are affecting, in this case, to the lensing, to the amount of lensing that you have that will boost or erase anisotropies. And this is like the decay of the potentials also will provide less lensing, and then will boost the anisotropies, compared that we can see in the red line, compared to, for example, the purple line, in which if we include the perturbations mass, it's going to erase the perturbations a little bit. And due to the fact that neutrinos cluster, and then like we have more lensing, less decay of the gravitational potentials, and then more lensing. And basically these are the main effects that are affecting the spectra. And the main conclusion from here is that high multiples provide a measure of the background, and intermediate multiples measure better the mass of perturbations at this level. It's not a statement that is 100% like this, because there are different degeneracies, as I've said, and there's a lot of things going on here, but more or less this is what's happening. And now just moving to the results. Here, what I'm showing is the posterior distribution that we found out only for we only included the CMB of Planck 18. And here, what we obtained for the background mass is that the shape of our result that is shown in red compared to the standard Planck result that is shown in blue is that the background mass shows the same behavior in our case than the standard neutrino masses in Planck 18. And then at the perturbations level, we can see that, for example, like the blue is the same, the blue line is the same one as here, because it's the same result in which background and perturbations are the same. But it shows a very different behavior compared to the perturbations mass that we obtained. And yeah, mainly our conclusion here is that the background limit is basically the same as the Planck 18 one, and the perturbations one has been relaxed by a factor of 3. It's less than 0.8 at the 95% confidence level. And we also saw here that a degeneracy appeared And basically, this is because of the intermediate multiple degeneracy that is also seen at high multiples with the lensing. And yeah, we find that these two masses have a mild degeneracy because it's not perfect, but it can be seen in this case. And also, I haven't said it, but this line will correspond to the case of the same background mass equal to the perturbations mass, so the standard case. And the final thing that I want to say about this figure is that you may focus on this peak, and that could be like saying, okay, is this a mass? Like you are claiming something. We're not claiming anything. We're just say, I mean, we think that this is just a lensing anomaly feature because Planck 18 like has the lensing anomaly at almost 3 sigma level, and since Planck 18 wants more lensing, a way to compensate, as I explained with the effects before, is also increasing the perturbations mass. So we think that this is a feature of the lensing anomaly. But the main takeaway message from this is that the current bounds that we obtain for neutrinos come from the background evolution. And just to finish, I am showing also here a triangular plot where I show also the degeneracy that you have between the background and perturbation mass with the sigma 8 and h naught, that are the parameters that are known to be degenerated with neutrino masses. And as we can see here, also the result is the same. Like the degeneracy of h naught and sigma 8 are also at the background level, because the blue contours coincide almost perfectly with the red ones. And the perturbations mass shows a very different behavior. So the degeneracies are at the background level. And here, more or less, like the question here is like, okay, let me say that, well, all the main parameters that I show in tension in cosmology seems to be degenerated at the level of background, so the energy density, so also neutrinos. And with this, I just want to conclude. And my final remarks are that, well, as I said, cosmological bounds on neutrino masses come from the background evolution. The standard constraints apply to the background mass, while the perturbations one just gets relaxed to 0.8 electron volts. That this is also a very good, I mean, let me say that this is also a very good measurement, because it's pretty much the future sensitivity reach of scattering. But still, it's a little bit more relaxed and not in tension with oscillations. And I guess that from this, one could say that if a model modifies the expansion history alone, you could evade the stringent constraints on these neutrino masses. So now it's your turn to think of such a model, and yeah, thank you.